Recordings rolling. It's Friday, March 7th, so we're going to continue review. You guys definitely have your notes out, right? You guys got some notes because just like the last few days, the solving some puzzles here. Right, so next week, you guys are going to be in school for 4 days. We'll be doing more review. I can pull some of
Which day is taken off?
Friday. Right, you guys don't have go on next Friday. Okay. I did throw the idea of giving you guys some in-class quiz type assignments where you guys can work in teams. I think actually I want to push that off until after spring break because we're about to, of course, go into spring break and close third quarter. And yeah, I don't want to end up in a situation where some of you guys end up with zeros in the grade book for that. So just to avoid that, I might push that off a little bit. Right. Now, my guys, my other classes today, actually, right. Well, here, my other class today are doing these new whales and venom whales. So, I'll show you guys this a little bit. I did doing that. Well, here, guys, these cards on your desk. If you want to keep this card, you can. If you want to put this together on your own time, you can. But really, this is just an activity to do in my other classes. Now, you guys, we're doing more AP review. But if you want to keep this, you can. All right. So, show you guys what this looks like and kind of what the principle behind it is here. So here's the principle. Did I show you guys this the other day? No, you haven't seen this yet? Okay. So guys, what three colors are in your color printer? Yeah, these are right here. You have a cyan, a yellow, and a magenta. Now, just from those three colors, you can make all the colors, right? If you don't print anything at all, you just get the white of the paper. And what if all three are going at the same time? What does that create? It creates black. Even if you don't have any true black ink, you can create black out of if you mix all three of these, right? Guys, how does your printer make red? Ah, magenta and yellow. That makes this red color right here, right? Right. So this is called subtractive color mixing. This is how paints work, your ink works, right? Anything that's like pigments, where white light will hit, say, like this page, and like this yellow here will absorb all the colors except for yellow, and that's what it reflects back out to the world, and that's what your eye see. Right? Now, there's a different kind of mixing that works with lights, right? Like turn on different color lamps. Or how about your phone screen? Because if you zoom down microscopic to your phone screen only has three different colors on it. What are those three colors? Yeah, RGB. Yeah, red, green, and blue. That's it. Yeah. How does your phone screen make yellow? Yeah, red and green. If you have red and green lit lights, that's how you create yellow. How does your phone screen create a white background? Yeah, that's all of them going at the same time. Creates this white right here. Right? What else we got here? Ooh, let's do this one. This one's fun. Guys, stare at that for about 30 seconds, and I'll tell you what's going on. So this is called retinal fatigue. Now, your eyes have three different cone detectors. Guys, what three color cone detectors do you have in your eyes? Yeah, RGB. Yeah, red, green, and blue. This was sort of like the primary colors of color addition. Right? Unless you're colorblind, you might be missing one of those. Right, so right now, your eyes are getting used to the colors that are already there. So when I flip the background when I put a white background there, you're going to see the opposite of what's already there. Kind of like this similar principle to if you walk in a bakery, it smells like bread, but hang out there for a while, you stop noticing the smell because your brain acclimates to your environment and your brain is really looking for changes. Right? You guys ready for this? I've never seen a purple apple or a blue apple, but here, from left to right, what color apples do you guys see now?
Yellow.
Yeah, there should be. Yeah, I think from left to right it goes green, red, yellow. That's what you should see. It only works for a few seconds, and it kind of fades away. Right? All right. So yeah, retinal fatigue. So that's fun. Okay. All right, so that brings us to this wheel. All right, so the side with all the colors on it is called Newton's wheel. So Isaac Newton invented this one. Now, what way I have this is here. If you want to put this together on your own time, you can't. Now, you do need to space this out a bit. That's what these separators are for this to work. Because if it's all flat like this, then when I pull the strings, it just wants to turn like this and it wants to spin about this axis, and it totally doesn't work. I want it to spin about this axis going through the center of the circle, right, like this. Right, so right, so cut a couple of holes, wind the string through, right, and then I can wind it up like this. Right? And if I get this going really fast, now you guys just a minute ago told me for color addition, if you add all the colors together, you get what color? White light, white light. Okay. And if you spin this really fast, sometimes it works better in person than on a screen, but let's see. Okay. Okay. Oh, yeah, no, looking at it right in front of me, like 2 feet from my face, I saw it turn white. Did that work on the screen? Let me look at the screen while I do that. Does it turn white? Yeah, it turns to a white color. You guys see that? Put all the colors together. Right, now on the other side, this is called a Benham's wheel. Now you guys see this is clearly only black and white, right? That's all it is, just black and white. Okay. Oh, but these stripes are a little bit different length. Now when I get this spinning, now this one works. I think if I spin it not as fast. Okay. And okay. This is one of these that works better in person than through a screen. Like I'm looking on a screen right now, it's not working that great, but 2 feet from my face, it's working pretty good. And it works for different people differently. And that's that illusions of colors pop up for these different bands. So I'll tell you what I'm looking at, just not through the screen, but just in front of my face in a real person. It looks like the inside band is kind of a dark purple color. Then it goes maybe like a green and then a gold and then kind of a dark red color on the outside. Although, and I don't know why this is, but when I turn it clockwise versus counterclockwise, I see different colors too. Right, so the idea here is that colors don't actually exist in the real world. Like there are no, oh, there's a red proton, right? That's not a thing, right? There are wavelengths of light, and then your brain interprets that as color. So the colors are really created in your mind, right? So here, yeah, so your brain can perceive different, or your eyes and your brain together can perceive different wavelengths of light. Come to this, right? All right, so yeah, so there you go. If you want to keep the card, you can. I printed out plenty of these, so I have enough for you guys if y'all want to keep those.
Is that like an effect that
yeah, it's called. I know it's called Benham's wheel. You can look that up. Yeah, so that's with my other classes. All right. Okay, so one more thing is the last day of school before spring break for you guys. Last day I'll see you is March 13th. All right, so here, give you guys an option. What do you want to do on March 13th? We can just keep doing review all the way till spring break, or we can take a day and do some songs. Well, let's do both. We'll do majority rule. Here's the songs. If you guys want to play anything, you guys can play something. I'll play something. I don't know how you know about that song, but yep, that's on the list. Yeah, we'll do it. All right, so who wants to just do a review all the way to spring break? Vote for review. Got 1, 2, 3. All right, so I got 3 on review. Who's voting for songs? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 10 to 3. Looks like we got a song day coming up. All right, you guys got paper out for notes. Paper out for notes. Again, if you guys want to play something, then I'll have a guitar and I've got a piano in here anyway. All right, so last time I saw you guys a couple days ago, we started to go through this rotation stuff. Now, there's a lot involved with rotation. We got centripetal force. We'll also bring in gravitation and make orbits. So we're going to work towards that. Do you guys remember this poster right here? Yeah. Okay. So, and there were a few after that. I'm going to backtrack a little bit and have you guys solve some of these. So I got this marked up. Suppose I got this mass right here, which is 100 grams. Isn't that 0.1 yeah, 0.1 kilograms? You guys, 0.1 kilograms. On a string, say I cut a string that's 70 centimeters long. I'll call it 0.70 meters. Just have it in base SI units, save you guys conversion. Okay. So here's mass in kilograms. Here's the length in meters. You guys read those numbers? Okay. And what if I get this rotating in Earth gravity? Let's go ahead and use 9.8 meters per second squared today. Right, precise one. And I take a protractor and I measure this angle from the vertical and I get 29 degrees. Right. So do you guys see 4 given values? You got this mass, this length, this gravity field, and this angle. You guys got all those? Okay. Yes. I want you guys to figure out these. Here's my 3 questions. What is the tension in the string? So if I put a spring scale here, what's the spring scale going to read? What's the tension in the string? What is the linear speed? I might call that the tangential speed of this mass. And how much time does it take to orbit once? Let's call that the time period. Okay. So you guys solve it, I'll solve it. And let's see if we get the same thing. Here, I'm going to solve it off screen while you guys are solving it, so I can paste this out correctly. See if we're all getting the same thing here. About to be making a free body diagram. So I grab this ruler. Let's have a free body diagram. All right, I have answers to all those three questions. So, how about you guys? How about first one? Who knows what is the string tension? Who knows the string tension right now? Who knows the string tension? Okay, keep going then. Keep going. I'll wait for somebody to at least get the string tension before I start solving this with you guys. Did you guys make a free body diagram on that lab mass down there? And what forces are on that lab mass? How about now? Who knows the string tension? Nobody's got string tension yet? Here, help you guys frame this a little bit. Guys, what if it wasn't swinging at all? What if you were just holding it at rest? In that case, what would the string tension be pretty close to?
Gravity.
1 Newton.
1 Newton. Yeah. Guys, wouldn't it? Doesn't that mass 0.1 kilograms weigh approximately 1 Newton? Right. Now, if you use that gravity field 9.8 meters per second squared, you actually get like 0.98 newtons. Right. Now, if you're rotating it, is the string tension going to be a little bit less than or a little bit more than 1 Newton? It's got to be a little bit more, right? Because now it's going in a circle. Oh yeah. I guess not quite that big.
Yeah.
Here, if you guys set up a free body diagram, then you can solve it in one step with trigonometry. Might need a cosine, maybe. You guys remember cosine? I know I've seen AP ask a really similar question to all this before for free response question. I forget if it showed up on an official exam or if it was just on their practice materials, but I know AP has asked pretty much this before.
Oh.
Aha, Alec got it. Aha. 1.12 newtons. 1.12 newtons. All right, so here, I'll start walking through this with you guys. Oh, I got my answers down here. Let me fold this corner. So, you guys came up with this as the free body diagram. The weight's straight down, and the tension force is up to the left. At guys, what angle is this right here? It's also 29 degrees. Okay, let's go 29 degrees that way, but yeah, it's also 29 degrees from the vertical. Okay, so I'm going to dash this tension force into components. Say, well, that tension force is doing two things. It's holding the weight up against its own weight, and it's also pulling that weight in to provide some kind of, hey, would this be like a, this component be the centripetal force it could be?
It's gonna be.
Oh.
Now, looking at this vertically, can you guys say the sum of the forces in the y direction is equal to what? 0. 0 newtons. Right? So that's this tension force time here. Maybe let's try to squeeze this in here. This is Ft times what? Cosine of 29 degrees. And well, I guess I could call this Ft sine 29 degrees. That might be helpful later. Okay. So Ft times cosine of 29 degrees. That's what's holding it up. Okay. Minus mg pulling down. Actually, let's throw a number on this mg. What did you guys get for mg? Yeah, 0.98 newtons. Okay. And you guys got that by doing m is 0.1 kilograms times g is 9.8 meters per second squared. It gives you 0.98 newtons. Okay. So subtract off that 0.98 newtons. That gives you 0 newtons. Okay. So add this over. So tension force then is going to be 0.98 newtons divided by cosine of 29 degrees. And calculator 0.98 divided by cosine 29 degrees. Oh, yep, 1.12 newtons. There you go. There's the tension in the string. So if you say cut the string and slip in a spring scale is going to read 1.12 newtons, right? Which is a little bit more than the weight of the lab mass itself, right? So you guys get so far. Everybody good with that? All right, so check this one off. Linear speed. Help you guys out a little bit. What formula do you think can connect forces to speed moving in a circle? What formula are you guys going to use? Centripetal force. And how does that formula go? Yeah, force is equal to mv squared over r. Here, I'll write that down. I'll do F sub c for centripetal force equals mv squared over r. Okay, so that could be helpful, right? All right, you guys write that down on your paper? Or hopefully you know it, right? Hopefully you know that. Okay. And then on the AP equation, they give you centripetal acceleration is v squared over r. So maybe you can start from that. Okay. Here, I'll fill this back on the board. Okay. Now I'm going to double check my work while you guys are solving for linear speed. See if I got what I got before. I got before. Yeah, okay. I got the same thing twice in a row, so that's probably it. Okay. That's fine. I'm gonna orbit. Let's see what the orbit would be.
Taking this one for the sake of the around. I'm gonna want
Okay, here, I'll send that. Oh yeah. All right, Alec got the linear speed. Anybody else get the linear speed? Both got linear speed. Right, here, give you guys a little more time. One more time.
Yeah. I'm sure.
Why are you so evil?
Four people different one where it's around divided by zero value. That's the radius. No, the radius is 0.7. Yeah.
Which gets. Ooh, I got a little slower.
The radius is 0.7.
That's not too far off though.
That's just the length. Yeah. The radius.
The radius. You have to do side.
Oh, right. I keep for. Yeah.
Give you guys a little more time. Who else can catch up to Alec here?
Yeah, I keep forgetting to put it in there.
That's what it is.
Like in meters per second. Like how fast does it go on meters per second?
What else would it be?
Yeah, so if I point a radar gun at that lab map, oh yeah.
I'm working on that one.
Teacher?
I think I'm the radius.
It is, though, it is.
Here, tell you what, I'll start working through it because there is a middle step. Before you can get linear speed, actually, you know what, you do have to solve for something else first. What do you have to solve for? Yeah, radius. Yeah, this radius right here. We go ahead and put this on here. So, how can you get this radius?
29 degrees times 0.7.
Exactly. Aha. Yes, this radius. Well, here I'll just label this R and then this over here. Yeah, the radius would be L sine theta, wouldn't it? Right. So L is 0.70 meters. Sine 29 degrees. So what is that radius? What is 0.7 sine 29? That is
0.3 yada yada yada.
yeah 0.339 meters. Okay, so that could be helpful. Okay. Now that you guys know the radius, give you guys a little more time, one more shot to get that linear speed. You got it?
I'll show you.
Yeah. All right, Hector got it. All right, Alec got it. Hector got it.
Or this. It's 2 times. So at least plug in the. It's 2 pi square root of length over
Right.
What's the last? You don't need it.
All right, you guys ready to start going with this? Yeah, let's do that then. All right, so I know centrifugal force is mv squared over r. Now, centrifugal force is related to this tension. How? Guys, how is this centrifugal force related to the tension? Yeah, it's a sine relationship. So I'm going to take the centrifugal force of 1.12 newtons and multiply by sine of 29 degrees. Sine 29 degrees. Okay. Now that component of the tension represents the centrifugal force. Is that okay? Did you guys see that? Right. The tension is doing two things. The tension is holding up the lab mass against its own weight. That's how we figure out what the tension was in the first place. Right. And it's also holding the lab weight in a circle. And that's this horizontal component, which is the sine component of the full tension. Okay. Or you could take the weight and do tangent. Guys, could you take the weight and do times tan 29? And that would also represent centrifugal force. Okay. That's an alternative way to get there. Right. I know the lab mass itself is 0.10 kilograms. We're solving for the speed. Now, here the speed is squared. So already I know the last algebra step is going to be a square root. Right? And it's all divided by, and here's the radius, 0.339 meters, which is L sine theta. Can you guys algebraically rearrange this and solve for V? Okay. All right, so I'm going to take here, I'll just do this on my calculator. 1.12 newtons. Let's round it a little bit. Okay, so it's close enough. Times sine 29 degrees. Let me say that. So that's 0.54 newtons is the centripetal force. Right? Cross multiply 0.339 meters radius. Divide down 0.1 kilograms mass. And guys, what's the very last step again? Algebraically, I have to do what? Take the square root. Yeah, guys, this number on my screen right now is equal to V squared. So I have to take the square root of that. Right, so the algebra steps later. I'm getting 1.357 meters per second. Actually, I don't know that level of precision. Maybe we can say 1.36 at best, but
Yeah, because.
something like that, right? Okay, about 1.3 something. Yeah.
That's not. That's not-
For right here? Yeah, okay. So here, go back to here's my three value diagram. Okay. This component right here is acting as the centripetal force. Okay.
Oh, yeah.
And what that component is it's the horizontal component of the tension. So once you know the tension, which was the answer to the first question, okay, and you know this angle, which is 29 degrees, then treat this as a hypotenuse, multiply by sine of 29 degrees, and flip over opposite, and give you this component, which is horizontal. Right.
Oh, okay, that's the.
Yeah, and that's what's holding it in this horizontal circle.
Okay.
Okay, horizontal circle? Yeah. Yeah. All right, so everybody see that? Yeah.
What if the center column of this, where it's turning on, isn't parallel with gravity? What if it's like off to the side?
Oh.
Is that like PhD physics or?
Okay. All right, so the question is, what if this is like tilted at like 30 degrees this way and it's going kind of off the side? Yeah, I've never thought too deeply about that. I think that would be pretty complex. Yeah, I don't think he's gonna quite go that deep. Yeah, I've never seen anything quite that complex. But yeah, hold on to that question. That could be a good one. It's my own time there. All right, so is everybody good so far? Good so far. All right, so last question then is, how much time does it take to orbit once? How much time?
Oh, that
All right, so guys, go ahead and solve. How much time does it take to orbit once? We'll call that the time period.
Is it velocity over time or? It's. Okay, I've got it.
There we go.
What was there again?
Aha, Luke got it.
Oh my gosh, the first time ever.
Like he's making a word.
I can do geometry, guys.
We're a little bit faster than that.
So x squared plus y squared divided by speed.
Yes.
How did I get on that?
Yeah.
Anybody else got it? Anybody else?
There it is.
All right. So, guys, picking up from the speed, because you need this to get the third answer. Oh, guys, could you call this pretty well a constant speed going around? Constant speed? Is that okay? Yeah. Is that the same thing as constant velocity? Yes or no?
No.
No. What? Why is okay? No, it's constant speed, but not constant velocity. Why? It's changing direction. It's on a curved path. Okay? But we can go with the speed, right, and say it's going to go some distance around the circle. Ooh, what's that called? Distance around a circle? Circumference. And what do you guys know a formula for circumference? 2 pi r. Right. Here, just a real fast recap. That's different than the area, cross-sectional area of a circle, pi r squared. Right. So remember, circumference is proportional to r. Area is proportional to r squared because it's like an area. Right. Now you actually don't need this one. Right? Oh, I know. Distance equals speed times time. Is that true? Okay.
So, like from an outside perspective, it doesn't have a constant velocity because we can see it changing. But like if you had the perspective of the cube, wouldn't you say you had constant velocity?
You could say constant angular velocity.
Okay,
do that.
then wouldn't
Yeah.
we as humans have constant angular velocity and everything else on Earth? Or Because like we're going in a
Oh, okay, yeah, so you're saying the fact that we're on a giant spinning globe, right?
Yeah.
And which is also revolving around the sun and so on. Yeah. So guys, if this is the whole Earth, that is true. Yeah, just focusing on the Earth itself, just the fact that the Earth is spinning, yeah. None of us have a true constant linear velocity, okay? But it's approximately true. Because guys, how long does it take the Earth to go around once?
24 hours.
24 hours. So, guys, if you actually watch the model of a globe spin around in 24 hours, it might be kind of difficult to tell it's even moving. Like if you saw a hand on the clock and you watched it, it took a whole day for the hand to go around. Like, can you guys see that hour hand moving? Who sees the hour hand moving? It's like nearly impossible. Right? So could your speed be approximately linear? Yeah. So it's one of those approximations. It's like saying, if you fire a cannon, is the ground pretty well flat for a few miles around you? I mean, pretty close. Okay. Yeah, so we do some simplifications. Okay, so this is going to be the distance it goes around is going to be the circumference. So I'll substitute in 2 pi r. I know the speed it's going. We have a number for that. We just answered that. And this t, I'm going to change to a capital T for time period. Okay? Not to be confused with tension. That's why on the tension, I label it F sub T for tension force. Right, so you don't mix it up with time period. Okay, you guys okay with that? Yeah.
Multiply by the radius. Are you getting rid of the fact that it's in radians?
Well, the radius could be in meters, right? Here, okay, so guys, here's another recap. Angles could angles be measured in degrees? Angles could also be measured in radians, right? Okay. 1 radian as an angle is equal to about how many degrees? Like 57 degrees, about 57 degrees. Okay, those could be approximately equivalent. Right? That's different than radius. Right, so radius can be measured in like inches, meters, that sort of thing. Okay. The idea of 1 radian is like if you took 1 radius and you take that distance and stretch it around the circle, this would be your 57-degree angle. Okay. So that's separate too. Okay, so all you need here is radius could be in meters. And we figured before, what did we write before? It's 0.339 meters. So 0.339. This is meters. Okay. I know it's swinging around at this fast, 1.357 or so many meters per second for some time period. Okay, you guys see that? Distance equals speed times time. The distance is the circumference. Okay, so let's do 2 pi times 0.339 meters divided by 1.357 meters per second. I'm getting a time period of 1.57 seconds. Aha. Okay. You guys go with that? You guys can solve that? All right. So let's do a recap here. Okay. I gave you guys a conical pendulum. I told you the mass of the pendulum, which, well, here guys, I got another question for you guys. Guys, here's another question. Suppose I replace this little tiny mass right here with this big old mass. I just did 10 times the mass. You guys see that? I just did 10 times the mass. What changes and what stays the same? Does the string tension change? Yes or no? Yes, by a factor of 10. Yep, be 10 times the tension. No, to maintain this 29-degree angle and all these other given values, this length, this angle, this gravity field, although I did 10 times the mass, is it the same linear speed? Turns out it is. Turns out that the mass cancels out by the time you get to that point. Okay, and would it be the same time period to orbit once? Yeah, so that would also be the same. Okay, so if you swap out the mass, you can show that the tension would change, but these other ones would stay the same. Okay, right. All right.
That's the thing that I do.
You guys good on the conical pendulum? Okay, looks like that was a pretty good exercise. All right, I know we only got a couple minutes of class left here, so let's see. Yeah.
Oh, thank you.
Well, how about this? Since we only got like 90 seconds left, here, I'm just going to recap the last few posters that you guys saw the other day because I think worth your time to see them again. Right. So you guys could set up a system of equations for conical pendulum, and we just solved a bunch of stuff on conical pendulum. Okay. Provide diagram with it. Right. Could you guys convert linear speed to angular speed if you need to? And because whenever you see a rigid rotating body like this O'Neill cylinder, like a turntable, oftentimes it's more convenient to solve in terms of angular speed omega rather than linear speed v. Right? If you have a point mass on a string, maybe you want to stick to v. If you have a whole rotating rigid body, say we've got a ladder going across, it's probably omega. Right? There's reasons for that, but that's a good rule of thumb anyway. Speaking of rigid body that involves omega, I know you guys saw this one the other day, right? Now, if I had more time, I think I'd probably throw some numbers at you and have you guys solve this too, but you guys should be able to solve this one. Okay. Solve for the coefficient of friction. You give a spin, one slide's off. Okay. And this is the last one you guys saw also the other day before the SAT. Here, guys, let's walk through this. So, car's going around the banked racetrack, and there's some radius of curvature that goes to, well, here's the axis that it's all rotating about, way over here, right? Okay. Here's your radius of curvature. Okay. How fast does the car have to go so that it's not kind of drifting up the track and it's not really drifting down? So my free body diagram looks like this. I got two forces. Actually, this is really, really similar to the conical pendulum. But instead of a tension force in a straight, now it's a normal force from the road. Right? But otherwise, what follows really similar. So I know that this component right here, which is the normal force times sine of this angle theta, is mv squared over r. By the way, is this theta theta? Same theta? Yep, same angle. Right? Okay. And what else do I know? I know that this would represent the centripetal force, which if you know the weight of the car, that's balanced out by this vertical component here. So if I want to translate this to that mv squared over r, that's the weight times tan theta. Right? If you want to go from this leg to this leg, that's a tangent relationship. Right? So you could solve for the mass of the car cancels. So if you have different mass cars, they all have the same solution. Right? If you're a traffic engineer one day, you could solve for what do you have to set the speed limit to so that if the road is iced over, the car can still safely make the turn. All right, yeah, they're not ringing bells today. So you guys have a good weekend. I'll see you on Monday.